Greetings, class. Good to be with you. This is the lecture notes for Whitlock Schluter Chapter 2. And my pattern is going to be that the first line in the notes is the title given in the text. The second line is my more descriptive statement of what is actually in the chapter. Now, this is about displaying data, tables, and graphs. And just a few definitions here. A chart it's a generic word. It doesn't have a lot of information content. Pretty much some type of pictorial summary of some information. A graph, on the other hand, actually has a connotation of an x and y axes. Could be more than that if you went into higher dimensions, but that's our connotation with the graph. And then with the plot, you're connoting at least one axis here of an x, and then a lot of times you'll be thinking of points or something for a plot. Could have a y-axis, but that's the idea there. Now, the big deal. Why so much emphasis on graphs? Well, first of all, the three key features of a data set, we have shape, center, and spread. My three S's. Okay, we've talked about center and spread back there in chapter 1. Shape is a pictorial idea. We're going to get into that as a probability distribution later on in this lecture. But I'd like to just flip over to a Bible verse here. Genesis 3:6. When the woman saw that the tree was good for food, and that it was a delight to the eyes, and that the tree was desirable to make one wise, she took from its fruit and ate. And she gave also to her husband with her, and he ate. The focus here, woman saw that the tree was good for food. She didn't smell that the tree was good. She didn't, oh, it feels so good. No, she saw that it was good for food. And it's that sight that is our chief sense. So our eyes are our dominant sense by design. Dominant sense by design. Now, you've heard the quote, a picture is worth 1,000 words. Well, that's absolutely what we're talking about here. A picture is worth 1,000 words. Okay, now I've got Okay, now I've got 5 common charts, graphs, and plots listed here. Bar graph, histogram, box plot, line graph, scatter plot. These 5 are the fundamental 5 kinds of graphs. Now, there are 4 purposes for graphs. And if you can grab each of these 4 purposes, there are different ones of those previous graphs that serve each purpose. Okay, if you want to make a distribution of a categorical variable, bar graph is your choice. On the other hand, with the numerical variable for the distribution, it's called a histogram. There are a few subcases of histogram, namely a stem and leaf plot, and a pictograph that can be used, but histogram is the chief. Now, a box plot will also give you a distribution with less density, less information in it. Moving into relationships within a particular variable, let's say the hair color now, we'll use a pie graph for categorical, so pie graph or pie chart. Okay. On the other hand, if you have a numerical variable and you want to look at relationships within a particular variable, maybe we have height. We want to do height by major. This would be multiple box plot. See if there are perhaps the math majors are taller than the engineering majors, let's say. example, we're using that other category to distinguish groups within the height variable. Relationships between variables. Well, a contingency table is the first choice for categorical variables, and that is not a graph. Okay, not a graph. Also known as a two-way table. Whereas if you have two numeric variables, then we simply use a scatter plot. That will very nicely show the relationship between the two. And a trend over time, line graph is used on both. So line graph, line graph. Okay, that forms the core. There are many other kinds of graphs that can be construed as subcategories of those. And then there's some more kind of racy graphs that are more advanced ones we may look at later in the semester. Next, I'd like to show how to construct a histogram. I have a data set here. It's 40 observations of the gallons of gasoline used by commuters at a certain place. If I want to put this data into a histogram, then I have some steps laid out here. First off, we're going to select a number of classes, just arbitrarily picking 6. Once you have that number, then what we need to do is basically divide the data. I've got 30 to 3. That's my range there. So I'm going to take 30 minus 3 and divide that by 6. And I'm going to get around here. So we're going to round that up to a 5. So I want some bins or categories of width 5. Let's just take a look at the histogram itself. Here it is. So you can tell by these midpoints here that each bar has a width of 5 length there. Now, how do you get the numbers broken down? Well, the first number is 3, so I'm going to start off with a 3, and then I want to go 4, 5, 6, 7. So I'm going to go 3 to 7, and that consists of 5 numbers. So 1, 2, 3, 4, 5, 6. I have 6 values from 3 to 7, so I put a 6 in here. 8 to 12, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 values from 8 up through 12. Okay, and there's my 9. And so on. We can fill out the values in this histogram. This would be a good exercise for you to complete at this time. Go ahead and pause and do that. Once you're done, you're going to find out the following. This column should add up to 40. The midpoint here would be 25. Midpoint of 28 to 32 is 30. And then the relative frequency. This column, to get that 0.15, is 6 over 40. Okay, so down here I'm going to have 4 over 40 is going to give me 10%. So that's right there. And we'll put 3% here. If you add up this column, you're going to get 1.01. That 1 right there is due to round off. No problem at all. Okay, now we've seen what the values are. So I should have 6 on my first bar. Sure enough, first bin there goes from 3 to 7, and that goes up to 6. Second bin should be at 9. We can see that. That tracks over there to 9. Looking good. Okay. Now, we've got some scripts here on R. Let's go ahead and show those run. Do that. Bib onto R. S.318 Lecture Notes.R has these scripts in it. So I'm going to go ahead and just focus in on them. If you click the gas usage on your loaded data, then you'll see, oh, gallon, there's the 3 all the way down to the 30. Yep, sure enough, that is the guy. Coming back over here, let's go ahead and do an attach then. Attach gas usage. So now if I do gallon, then sure enough, Gallon has it. So histogram of Gallon gives me a generic histogram, looks good. 0 to 5, that's not exactly what I did by hand. And my labels are a little clunky. So I'm going to go up here and run the second one. Just click my run button. Notice I've added gallons here. It looks better. Distribution of gallons used by commuters. That looks great. If I want to fix the bins, then I'm going to just create this variable called bins. It doesn't have to be called bins. And ours histogram has the right endpoint as being in the bar. So if I want everything greater than 2 on the left, and then up to and including 7, next one is going to be greater than 7, up to and including 12, and so on. Then I can run a histogram, and the command is breaks. Okay, so I run that, and you'll notice this is the exact histogram that I got out in the lecture notes. Sure enough, that fixed it up nicely. Okay, last topic, raw materials / probability distributions. Remember that the raw materials of statistics are the data or the random variables, and so we want to take a little look at those. Now, random variable, as we saw last time, is the abstract concept we want to measure. Okay, it's a variable that can take on different values, but probabilistically. Okay, so let's just calibrate ourselves with respect to probability here. So p equals 0 means that something has a 0% chance of occurring, okay, which is impossible. So let's say impossible. 0.05, that's obviously a 5% chance of occurring, which is, let's say, very rare. 10%, we'll just call that rare. 50%, okay, that is common. And then 0.95 is a 95%. So let's call that very common. Now, a 1.00 is 100%, which is certain. Okay, so I have certain events. Now, there are some different kinds of probability. I want to focus on the theoretical and the empirical. Theoretical probabilities are also known as equally likely outcomes. These are probabilities that are purely based on theory alone. Okay, we're going to get to them in a sec. Whereas empirical probabilities come from actual data in the real world. Subjective, we won't really focus on in this class, but subjective probabilities are, let's just say, those that people estimate themselves. For example, expert testimony in certain domain areas can give you subjective probabilities. My focus in this section, there's going to be a lot of graphs, is to show you the common shapes. In fact, let me just run through them real briefly. There's a rectangular shape distribution. There is the mound-shaped distribution. And we have both the skewed left and the skew right distributions. So we'll go skew left first. There's a skew left. We'll do a skew right. And then lastly is the bimodal. These are the 5 common shapes that I'd like you to be familiar with. The key thing about them is that when you encounter a particular shape, it tells you something about the variable or its underlying distribution. So for example, this is the face of an ordinary 6-sided die that my daughter rolled 60 times. Okay, boom. You can see the outcomes here, and they're graphed in a nice histogram. Okay, roughly rectangular shaped. What's the message that comes out of that rectangular shape? It is that every outcome on the die has an equally likely chance of occurring. This is a theoretical distribution of that. Second shape is the mound. Okay, this is the UCR height data. And we can see that it's got this nice mounded shape. A special mound is called the normal distribution or the bell-shaped curve, which we'll talk about in Chapter 10. This is the breakdown of the probabilities in each one, which we could calculate if we made the histogram by hand. But the point is, there's a mound. What's the message that comes out of the mound? Here's a 5-coin toss. A 5-coin toss means that you toss 5 coins and you count x equals number of heads. We could have anywhere from 0 heads, 5 heads, 1 head, 2 heads, and so on. Okay. Here's the theoretical probabilities of that, which we could calculate. No empirical study done. What do we learn from a mound? We learned that there is a common center in that mound, and most of the data clusters around it, but there are some extreme values on both sides. IQ scores is another classic case. The center of the IQ score distribution is 100. Above 100 IQ is above average. Third common shape, skew right. Okay. This is a distribution, it's empirical, of the values of houses in Orange County in 2001. Clearly skew right. Now for fun, we're going to take the old 5-coin toss, but biased coin. P equals 0.75 of landing on heads, which means it's going to land on heads 3 out of 4 times. Okay, so out of 5 tosses, here we can see we're going to get more heads, or more frequently we'll get the higher number of heads. Skew left. Here's just a theoretical skew right distribution. And lastly is a bimodal. Oh, before we do that, what do we learn from these skew distributions? What's the message? The message is there is a point where things are clustering, but there's extreme values on one side of the curve, or one side of the distribution. With the skew left one, the extreme value is 0, and that may come up. Take a look at this graph. This graph is the full-time salaries of law school graduates, I believe in 2011. Okay. Wow. There's 2 very clear different mounds or groupings of data. So what that tells me is there's something in that population that's dividing it into 2 groups. Whether it's a distinction between elite law schools and those that are not, or kinds of law practiced, there's some distinguishing factor in that population. I'm learning that by the bimodal shape of the graph. Okay, few remarks you can read over on interpreting graphs, and that covers this chapter.